All right, everybody. Hope you're all doing well. So this is going to be the very first lecture video for chapter 12 here, right? Which is kind of the second part of this whole unit on solids, liquids, and gases, right? We just finished up chapter 11, which was specific to gases. Now we're kind of moving on to solids and liquids, and then talking about the intermolecular forces between solids and liquids. Okay, so without further ado, let's get right into it. Now, before we can talk about intermolecular forces, let's talk about the difference between intermolecular forces and intramolecular forces, right? So here is a couple of things regarding intramolecular forces. Right? They are the forces within the compounds or within the molecules, right? They're the bonds we've spent so much time talking about, right? Talking covalent bonds, talking about ionic bonds, right? So think about intramural sports being the teams within the school, right? So if you're doing an intramural sport, like it's called sometimes, right? That's talking about intramural being sports within that particular school, right? All the teams within that particular school. All right, they are the forces that hold together particles in a single formula unit or a single molecule, right? So for example, you've got the bond between H and H in a single molecule of H2. Another example would be the bond between H and O in a single molecule of H2O. I'm going to move myself up here, actually. Okay. So again, it's talking about the bonds that actually piece together the individual particles, individual atoms of different elements, right? So in H2O, in order to piece together an H and an O in a molecule of H2O, that covalent bond is an intramolecular force, right? Again, this includes covalent bonds. Now, what's the difference between intramolecular and intermolecular? Let's get into it. It's going to be the attraction between or among whole particles or whole molecules themselves, right? So when you've got more than just one particle of water, right? So I've got my water bottle right here, okay? In my water bottle is, of course, water. If I were to just have water inside of this thing, it's not like that. All this liquid water inside my bottle here is just one molecule of water, right? This is made up of like billions upon billions upon billions of water molecules inside of this water bottle right now, right? So whenever you're taking sips of water, even your one sip of water has probably got millions and millions of molecules of water, right? H2O molecules. Well, intermolecular forces talks about the properties and whatnot of, surrounding the, what essentially connects those molecules together, right? What keeps those molecules together depending on their states of matter, right? So it's the forces between multiple particles, multiple compounds, multiple molecules. And there's going to be three main types that we talk about during this beginning portion of chapter 12 here, right? The first one is called London dispersion forces. The second being dipole forces, so D-I-P-O-L-E is dipole. And the third is going to be called hydrogen bonds. Right, so London dispersion, dipole forces, and hydrogen bonds. Now there's this sort of umbrella term that we're going to also utilize called van der Waals forces. And this kind of is an umbrella term that encompasses all of the above, right? So it's except hydrogen bonding specifically, right? So van der Waals forces is more of an overarching generalized term for the London dispersion forces and the dipole forces that you can see in certain molecules, right? Now, whenever it comes to different types of these intermolecular forces, right? How do we determine if a substance has any of these? Well, it's very, very, very simple. Yeah, so it's very simple, right? It's all based on what the actual molecule is made up of, right? The different type of elements that are present, right? Elements and what their actual molecular makeup is of that particular compound or that particular molecule. Okay, so let's go one by one here and start to talk about each of these different types of intermolecular forces, right? Again, here's a little bit of a graphic kind of showing you the difference between intramolecular attraction, right? Notice how the arrow for intramolecular attraction is pointing to and from the actual covalent bond between the H and the Cl, right? So again, talking specific to just the one HCl bond, right? That molecule of HCl. However, when I talk about intermolecular attraction, right? That's talking about the fact that on this screen, in this graphic here, we've got 1, 2, 3 different molecules of HCl. And those little red dotted lines kind of show you the attraction between a Cl and an H of different molecules, right? Because there is still some attraction. There's something to be said between the fact that, yes, there can be a bond, an actual covalent bond between an H and a Cl. But since this Cl is already being bonded to this H, well, what happens if this Cl wants to be attracted to this H here? Well, that's what exactly gives a rise to our intermolecular forces and intermolecular attractions here. All right, so first one here is called dispersion forces. First and foremost, these are the absolute weakest type of intermolecular forces, right? They're weak forces resulting from temporary shifts in the location of those shared electrons, right? So the keywords here being shared electrons, right? And again, when we talk about shared electrons, guys, shared electrons only exist in covalent molecules, right? Covalent bonding, right? If you're talking shared, it's covalent, right? The other type of bonding we focused a lot on was ionic bonding, and there's no sharing going on there, right? It's a complete transfer of electrons. So this particular dispersion force is going to be specific to covalent bonding only, right? Now, all molecules have dispersion forces. It literally does not matter what type of substance you are. You can be, really, really intricate looking molecule, or you can be something as basic as H2, right? All molecules of any substance have dispersion forces. Now, how do you determine how great or not the dispersion forces are of any given molecule? Well, it's going to be based on their mass, right? So if you can calculate the formula mass of that substance, the greater that calculated formula mass is, the more powerful those dispersion forces are, right? So little, small in weight, right? Small in formula mass substances, right, that don't weigh a whole lot are going to have the weaker dispersion forces, whereas substances that have a higher mass, formula mass, are going to end up having more and stronger dispersion forces, right? Onto the second one, the second type of force here, intermolecular force, is the dipole-dipole interaction. Now, these attractions are going to be between oppositely charged ends of polar molecules, right? So specific to polar molecules. Now, those two words, polar molecules, should ring a little bit of a bell because that's something that we talked about a few chapters ago, right? So when it comes to determining if a molecule has dipole-dipole interactions, we have to first be able to determine if that molecule is a polar molecule. Now, the idea with these dipole-dipole interactions is that the negative sort of quote-unquote ends of molecules stick toward the more positive ends of other molecules, right? So if you look at all of these dotted lines here in this graphic here in the bottom right-hand corner, that's kind of showing you the attraction between a positively charged end and a negatively charged end of different molecules. Again, keyword here being different molecules. Now, the greater the difference in electronegativity, the greater the dipole-dipole interaction. Now, again, when it comes to determining if a substance as a baseline has dipole-dipole interactions, again, we have to just determine if that substance is a polar molecule or not, right? And that's something that we've had experience doing, and we can very, very easily do that by doing a couple of things. Number one, looking at the actual makeup of the substance, and number two, determining if that molecule is polar or not by going right to our reference tables. If we grab them right here, flipping all the way to page 13. If you remember, table number 3 right here, guys, is our identification table, right? Telling us if anything on the left-hand side follows this order, they are going to be polar molecules. Anything on the right side of this table are going to be in order, all of our potential polar molecules, right? So that's going to be a very useful table once again. It's going to help us determine if something is polar or not. Once we've made that determination, we can utilize our electronegativity difference that we learned how to calculate back in chapters 7 and 10, right? That's just as simple as going to table S, right, pages 10 and 11 in your reference table, and calculating that electronegativity difference, right? Looking at the table, determining what the electronegativity is of those particular substances, and then going from there. Okay. Now, the third type of intermolecular force here is going to be our hydrogen bonding. Now, before you even throw anything on the screen here for you, right? I know the name, right? It says hydrogen bonding. You're probably thinking to yourself, hey, any substance that has hydrogen in it is going to constitute as having hydrogen bonding. And that's almost true. It's less so, guys, about the presence of hydrogen in the substance and more so what that hydrogen atom is bonding to. So, for example, there are only 3 main elements that hydrogen can bond to in order for it to be determined as hydrogen bonding. So when it comes to these hydrogen bondings, guys, it's going to be these 3 different elements. If hydrogen is bonding to either fluorine, oxygen, or nitrogen, that's it. right? So if you have a situation where you've got this molecule here, guys, where either F, N, or O are being bonded to a hydrogen, being bonded to an H, that's exactly what we're looking for, right? So again, it's not just the presence of hydrogen by itself, it's regarding whether or not, first, is hydrogen present? If yes, then it could have hydrogen bonding. And second, is that hydrogen bonding to either a fluorine atom, an oxygen atom, or a nitrogen atom? If that's the case, you've got hydrogen bonding. If there is no F, O, or N present, then there is no hydrogen bonding, and it most likely just has dipole-dipole forces. Okay. Now, talking about the strength of these intermolecular forces, right? Again, talking with our very, very first one we mentioned at the start of this video was the dispersion forces, right? Those are our absolute weakest. So when we look at this stretch right here, all the way to the right here is our dispersion forces. Dispersion is the weakest. Moving on from that is our dipole-dipole interactions. Then the strongest covalent-based intermolecular force is going to be the hydrogen bonding, which we just talked about. And lastly are our ionic forces, right? Ionic forces are basically intermolecular forces between different ions in an ionic compound. And I know we've learned about this a while ago, these ionic bonds and whatnot, guys, but these ionic bonds are the single strongest type of bond you can have, right? Obviously, there's a lot of things that have to go into an ionic bond in order for it to be classified as an ionic bond, right? So it needs to be a metal or a non-metal, metal bonding to a polyatomic ion or a polyatomic ion in some case, right? So it has to be two different ions bonding together. That is the absolute strongest type of bond you can have that will give rise to an intermolecular force, right? But if it's not ionic and it's covalent bonding, well, that just means that hydrogen bonding is the strongest possible intermolecular force. Now, when it comes to intermolecular forces, guys, they can actually kind of help us explain certain properties of substances. So, for example, if I've got really, really, really strong intermolecular forces like hydrogen bonding or even this ionic bonding stuff, that's going to mean it's more difficult to actually break up those particles, and then therefore those substances are going to have a higher boiling point, they're going to have a higher melting point, and are more likely to be liquid or solid at room temperature. Okay. So again, the stronger the intermolecular forces are, the higher the boiling point, the higher the melting point, and the more likely that substance is to be a solid or liquid at room temperature. Okay. Again, the weaker those forces are, well, that means that if you just have weaker intermolecular forces, your boiling point's not going to be nearly as high, your melting point's not going to be nearly as high, and your substance will more likely than not be either a liquid or possibly even a gas at room temperature. Okay. Again, we'll talk more about this and look at some sample problems and examples when I see you guys in class. But for right now, that's the end of the video, and I'll see you guys in class.